I'm going to do one more reduction today. I was going to do two. I'm saving you the pain. We'll do one more reduction. And I want to introduce this by way of the game we played yesterday. So we'll start off with a game, a little light game, a game that introduces this idea of finding a kernel in a graph. So I'm going to remind you what a kernel is in a graph. A kernel of a graph is a subset of the nodes that somehow represents winning positions in a game. That if you put your opponent in one of those positions, they're forced to move out of that position to one of the non-kernel positions. And if you find yourself in a non-kernel position, there is always a way for you to make a move back into a kernel position. So every edge out of a kernel goes to a non-kernel. Every non-kernel node has an edge that goes back into a kernel node. Those are the basic criterion. So if I give you a graph, does it have a kernel or not? Some graphs do, some graphs don't. If you don't have cycles in a graph, if it's a directed acyclic graph, then it always has a kernel. But I should mention that a lot of graphs, even though they definitely have kernels, it's just too exponential to find them. For example, you all know how to play this game? Where you draw little lines and you make a box and you put your initial in the box. And if you make a box, you get to make another free line called dots and boxes. So I'd go here, and Todd would go here, and I'd go here, and Todd would go here. Doe, I'd go here, and put an S. And for Shovlin. Then I'd go here. Well, you keep going, and then you get a free move if you get a box. Now, actually, this game is not easy. And there's some very interesting strategies in this game, and there are good players of this game, and there are a lot of issues. But the key thing about this game is that if you make a graph of it, where each node is a picture of the board, and the edges connect pictures of the board that you can move one to another, then the graph of this game doesn't have cycles in it, right? Because the game just keeps going and going until it's all filled up. You never go back to a position. You never erase an edge. So this definitely has a kernel. The only question is finding it is very hard because even the game is given to you as 4 by 4. So the size of this game is 16. But the size of this graph of the game is huge. For many of these positions, you have, what, something like 20 possible moves, a little more. So the tree grows like this, and even though it's just 16 size input, the tree is very, very exponential. And just going through the graph that represents this game would be a tremendous amount of work. So even if you had a way of going through a graph in linear time and finding the kernel, it would be a lot of work here because the size of this graph is exponential in the board. It's a big, it grows like crazy. A branch of a factor of 16 to 20 every time.
Could you show us a kernel for that one?
I have no idea. It's huge. I mean, there's billions of, well, not billions in this one, but there's thousands probably of nodes in this graph. Think of all the different configurations of this board. We have 1, 2, 3, 4, 5, 6, 7, 8, 12, 16, 20, 24, 28. There's 32 edges, and they can either be there or not. So there's 2 to the 32 nodes in this graph. That's a billion, couple billion. So there's a couple billion nodes in this graph. And there's a kernel in that couple billion node graph. But we'd have to look through it to find it. We'd have to do something that takes about 1 billion steps. Even though
is a winning position?
Kernel is what you want to throw your opponent in. In some sense, it's a losing position. So the best way to get a sense of it, to remind yourself what a kernel is, in the game where you're taking 1, 2, or 3 sticks from a single pile, this game, start with 9 sticks. If you are given the choice to go first or not, you'll pick 1 stick and throw me into position 8, which is a kernel position. That means I'm stuck. If it's my turn and it's a kernel position, I'm in trouble. Wherever I go, you'll throw me back into the next kernel position. Wherever I go, you'll throw me back into the next kernel position, and that means you win. Okay? Who has questions about what a kernel is? Things in the kernel can't have edges connecting them, and anything not in the kernel has to have an edge to something in the kernel. That's the 2 rules. Yeah.
What about, I mean, if you had a game like tic-tac-toe, which you can always take to a draw, how...
I mean, how do you just... The idea of these game graphs is that every node is either marked, that there's some bottom set of nodes, some things without degree 0 that would be marked win or lose. So a game that has a draw just isn't well defined for this purpose. So think of games that only are winnings. You could redefine tic-tac-toe to say either you get 3 in a row or you get more symbols than the other guy. So then the guy who's X always wins. Other questions? Yeah, Teresa.
I'm sorry if I missed it, but
Yeah.
can you define the rules for drawing a graph to represent a game?
Yeah.
You have like instance,
Yeah.
you have players, you have moves, you have positions. Like, which of those becomes?
So let's do it with the dots and boxes as an example. Okay, so let's do it with a smaller dots and boxes that's only 4 dots long, just so it doesn't get to be 2 billion possibilities. So here's the start position, 4 dots.
That's the whole game.
That's
the whole game.
what the game looks like. It's a picture of the game, some representation of what the game looks like.
Each node is the whole board?
Yes.
Okay.
Yes.
That's a given.
Yes. And now we're just trying to represent, we want to be able to watch people play and show a map of their play on the graph. So this is the starting position.
Okay.
And now it's your turn and you choose the top edge. So the board looks like this. And now you're in this position.
Okay, but what if I choose something else? And do you do all the possibilities around the circle? that
You
I
bet.
choose?
All 4 possibilities.
All right. And you put those at one level. All the possibilities.
And then this has, it's not a tree because we don't want to duplicate any of these nodes. So if one of these happens to go back to one of these, we draw an edge. In this case, it's going to actually be a tree because there's nothing that goes back, I don't think, right here. But right now, it'll look like a tree.
Okay.
But every node represents a position. If there's a way to get from one position to another, you draw an edge, a directed edge.
Okay. You just go down and find the possibilities.
Right,
Okay.
right. So it's big. It's a huge tree for an example, even 4 by 4. This example is not so big. But. Yeah, Todd?
If you change nim to polite nim, where you don't want to take the last stick,
Yeah.
is the kernel the complement? Is the kernel the same and you just change the mean?
Yeah, Todd asked a good question. What if you change the rule so that the end is not to take the last stick, but not to take the last stick? Almost always, you can still find a kernel, but it isn't exactly the complement. The complement of kernels aren't always kernels in the opposite game. In the case that you're talking about, in this game, this simple game, where you just change the rule to be the one where you don't want to take the last stick, you want to analyze that? Analyze that. Who thinks they know? You think you know, Michael? What is it?
You just want to get, so the other, you just want to get to 1. Right. So you just add, so the numbers would be 1, 5, 9, so.
You want to put the other guy in a position where there's 1 left. In order to do that, you want to get him in a position where there's 5 left. So if you change the rule in this case, Michael's 100% right, the kernel would be anything of the form 4k plus 1. Okay? And in general, I can switch these rules and do all sorts of things, and finding the kernel becomes a more tricky problem. But what I'm going to do today is just quickly go over a really fun game, which is, in some sense, trivial because it has a kernel and it's calculatable, but it's a game that most people off the street haven't seen, and it's kind of fun to play. It's not obvious. So here's how the game works. Now we have many, many rows. This game is the real full-blown version of NIM. There's many variations of it, but this is like the classic version invented about 100 years ago. There's many, many rows of sticks, and you can take as many sticks as you want as long as you take them from a single row. Right? And you can have as many sticks to start at the beginning of the game. So we played a version yesterday with 3, 4, 5. We'll play this version again, but then I want to play a version with, say, 28, 15, 8, and 72, just to show you how the method works. All right, so let's play this just to get some intuition on the game, and then we'll play this, and I'll show you how you analyze the game and what the kernel is, just to show you an example of an interesting game that has an interesting kernel which doesn't scream out. And when we're done with this, we'll go and do a reduction and show that kernel is NP complete. And you're going to find that in our reduction, we definitely have lots of cycles. Cycles are the key in our reduction, which means, well, which is a good sign, because there's no way we would show NP complete for kernel without cycles, because we know that that's easy. We know that that's automatic answer of yes. So we'd expect cycles to show up in the reduction. All right, so let's play this game. I think Doug played this last time and made a good first move. Anybody remember what it was?
2 off the top.
2 off the top. So now it's 1, 4, 5. What's the next best move? Actually, at this point, I think I've lost with 1, 4, 5. But I'll take 1 from here. So now it's 1, 3, 5. What's the right move now? Forgetting it, don't try to think up any strategy. Just try to
2 off the bottom.
think up a neat idea. So if Michael takes 2 off the bottom, it's going to be 1, 3, 3. And here's a little, this is a very, very special subcase of the game. But if there's ever equal piles and just 2 piles left, then I'm in great shape if I can give the move back to you. 2 equal piles left. Whatever you take, I'll just match it the whole way through. So if we take 2 off of here and there's going to be 1, 3, 3, then I'm just going to take that 1, throw it back to you with 3, 3, and sit back and match you the whole time. So if you try to just avoid that, you might be able to find the best move.
Take 3 off.
So now it's 1, 3, 2. So now it's my turn. If I take 1 from here, you guys can throw me in with 2, 2. If I take 2 from here, you can throw me in with 1, 1. If I take all of them, you can throw me in with 1, 1. So forget that guy. What about here? If I take 1, you'll throw me in with 1, 1. If I take both, you can throw me in with 1, 1. Whatever I do now, I'm dead. Now, that's the first thing a beginner who plays this game starts to realize, is that 2 equal piles, when you're all done, is part of the kernel. But it's only part of it. It's not the whole thing. In fact, an even number of piles that are equal, pair up piles that are equal, that's good, because you can just match the piles in your head. If someone takes from this pile, you match it on the matching pile. If they take from this pile, you match it on that matching pile, and keep everything the same. But that's just a special case of the kernel. The kernel here is really hidden in a really clever way. And it deals with binary numbers, so in some sense it comes back to computers. And I like this problem, and it relates to complexity, so we'll go through it right now. Let's do this game, and I'll show you where the kernel comes from. The way you do this, and you can write a program to do this and give it to your little nephews and nieces and children, because it's fun for them to play and learn this game, is you write each of these numbers in binary. You can all write a program to do that. You can all do it in your head, so help me, because I'm slow. What's 28? One more 0? No. That's it? Okay. 15. 8. 72. 64. No 32. No 16. 1 8. No 4s. No 2s. No 1. Okay. You write all the numbers in binary. And then you do something that seems very unusual, but when you think about it from the kernel point of view, it won't seem so strange. You look at these binary numbers, and you look at them in columns. Maybe it'd be helpful to actually write them in columns. Look at each column and mark to yourself whether they're even or odd number of ones. Okay, so this is an odd number, an odd number, an even number, an even number, an odd number, an even number, and an odd number. Okay? Just count how many ones there are. If there's no ones, that counts as an even number of ones. Everybody with me so far? You could all write a program to do this, if you tried. This value will help you figure out whether you're in the kernel or not. If these are all even, that's a kernel position. If they're not, it's not in the kernel. So how can I convince you of this? The first thing I have to convince you is that the winning positions are included by all the even. What are the winning positions? It's when there's no sticks left. Well, there's an even number of ones in 0, 0, 0, 0. So that's for sure. We need to check 2 other conditions. We need to check that if you're in an all-even position, whatever you do gets you out of an all-even position. Why is that true? If it was all even, how come whatever move you make changes that so that it's not all even anymore?
Because you're going to take from one row, so you can address.
You're going to take from one row. That's the rule. When you take from one row, what happens to this binary number? Some of the ones and zeros change. right? You can't keep them all the same. Whatever ones change, that column changes parity. So what used to be even then becomes odd. Whatever you try to do. As long as you don't let somebody take from 2 rows, because then they could change the parity twice and it could go back. But if they take from 1 row and it was all even, then they're going to be stuck and they have to go back to odd. And we'll see an example in just a second. But here's the harder part. You're not in the kernel. How do you figure out a way to get back in? This is very computable. This is not anything abstract. We're going to actually do it. We need to turn all these odds to evens. So go to the leftmost one. Go up. We definitely have to change this guy. That means we have to take from this row. Go to the leftmost odd that you have to fix. Find a 1 in that column. And now we're going to work on that row. And we're going to change bits as we go along to make all the odds turn to evens. So watch. This guy turns to a 0. That's okay. This guy has to turn to a 1. This is okay. This is okay. And these two have to turn to 1. What is that number? It's 11011. That's 3, 11, 27. So my first move is to turn this 72 into a 27. And now I have 11011. Is that it? That's 27. I got too many zeros in here? Too many ones? 24. 16, 8. 0, 1, 1.
Like the 28.
Like the 28. Okay, here we go. Now, if you add these up, we should get all evens. We just figured it out so they'd be all even. So let's mark it up. Even, 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 even. That's back in the kernel. Not multiples of 4 anymore, but even numbered 1s in each column. Now it's the bad guy's turn. Let's see that whatever we do, it ends up changing this. Well, pick anything. Say, take 1 away from the 28 row. That means one of these zeros and ones is going to change, and that'll turn to odd. So whatever you do, you end up out of even, and every time you end up out of even, I can throw you back in. There's nothing special about this except for the fact that I can throw you back into it when you go out, and when you're in it, you have to jump out. Exactly what a kernel is all about.
Because that's the final position.
Okay, so what if I made the final position like a single stick? I switched the rule. Would all odd work then? I'll let you think about that, because there's some subtleties with all odd. There's something with all even that's a little better. Here's an example. Say I had a whole column of all zeros. Right? That's even. Now, if we were trying to get something back to all odd and we had a column of all zeros, we'd have to somehow go to that column of all zeros and change one of them to a 1. But it's possible that that's going to end up adding instead of subtracting. Now here that didn't happen. There's a reason why it didn't happen, but you have to kind of argue carefully that this is a kernel. And I don't want to get too much into it. It's a fun area, it's a neat game, but it's getting a little off topic. It's just cool. I wanted to show you a neat example of a graph with a non-trivial kernel. And that's how you play it. And you can write the program and give it to your nephews for Christmas.
Isn't then just whoever moves first can always put the other person in the kernel?
Depends whether the position is a kernel to start or not. Like what if I started in this position? I said 28, 27, 15, and 8. And I go, let's play. Do you want to go first or second?
Yeah,
The chance of that happening is pretty slim, though. You figure you have a 50% chance for even or odd, then you have like 5 different.
Oh, well, so that's interesting. So Michael is implying a really good question here. what's the chance of you being in the kernel? What percentage of these nodes are in the kernel? Is it equally likely to have all evens and all odds? Is it equally likely for the mix of odds and evens? I don't think it's an obvious question to answer. I don't think it's obvious. I mean, I think there are fewer nodes in the kernel than there are not in the kernel, but I'm not at all sure what the percentage is. I don't think so, because I don't think that these E's and O's come with equal frequency.
How come?
These numbers are random, but if you take a bunch of random numbers and you add up the ones in them, it's not clear to me that every sequence of evens and odds comes with the same frequency. It may be true, but I'm not sure it's true. We can come up with let's do an easy example. Let's take just the numbers, say, from 1 to 3. I don't know, 1 to 2 even. So here are the possibilities. 1, 1, 1, 2, 2, 1, 2, 2. Let's say we just have 1 and 2. So this is even, even. This is odd, odd. This is odd, odd. Even, even. It's 50% there. And we don't even get any odd-even combinations. So the way these numbers combine to get odds and evens in the bottom is not at all the same as just give me a bunch of random O's and E's.
I bet though, over adding it up over that, if you take one and just 0 and 1 and 2, you're gonna get. I really think it's got to be close to 50-50. That's already
50-50 all evens versus 50-50 all odds?
No, like I think when you have you have 5 numbers on the bottom.
Yeah.
And I really think whether it's even or odd, there's a 50-50 chance. I mean, you saw when you did that, when you just did that, there were a total of 4 evens and 4 odds. And so,
but it's not just all evens or all odds. It can be E's and odds, evens and odds mixed together.
and that's not in the kernel. Then. You have evens and odds mixed together. So
Right. So it wouldn't be 50-50.
It's a 50-50 whether it's an even or an odd. And so if it's a 50-50 whether it's an even or odd, the chance of getting all evens is very slim. So chances of actually...
Do you think it's a 50-50 chance coming down here that it's an even or an odd? I'm not sure about that. Probably, but I'm not
How
sure.
many rows there are?
What?
How many rows there are? You have 5 rows.
Yeah, if you have an odd number of rows, it's not going to be 50-50.
Why not?
Depending on what the numbers go up to. If they don't go up to a power of 2.
Right, because you have all these zeros out here.
Yeah.
So
But the thing is...
if I have one number left, if I have just one row, then it's a 50-50. But I don't know.
Even if you have one row, the chances of that one number being in the kernel are slim. They all have to be zeros. If you have one, right? You're just doing one. If you have one row, 1, 1, 0, 1, 1, you're not in the kernel.
No, that's one column. That's not one row.
You just said row.
Right, but you're only going to, if you have one row, you just have one number over here. So
For each spot. So you have each.
right. So that's the only case that I see it's 50-50. But once you have, say, 3 rows,
Exactly.
I don't think it's...
The bottom 5, I'm not going to...
Here, if you have 3 rows, just write all the possibilities out. What did I miss
The
here?
chance of that being a kernel is there, slim enough. Because you know the first column is odd.
Here, these are all the possible combinations when you have, for the last thing, when you have 3 rows. So how many of them have even number of 1s? This one does, and this one does, and this one does, and that's it, right? So it's 1, 2, 3, 4, 5. Which one am I missing?
It's got to be 0, 1, 1.
0, 1, 1.
So half of them, that's what
Right, so half of them are even, and half of them are everything else.
Yeah, and so the chance...
But that's not obvious. You're saying that evens are the same as all the odds, but it's not the same. In this case, they're the same as everything else.
It's like 45-55% chance. The chance of getting all evens on the bottom to start off in a kernel position is very unlikely because you have 5 numbers. It's 1/2 to the 5th. So 1 out of 32 chance of you actually.
It's not.
starting in a-
It's not that. I don't think. We can do a test. We can do a program and actually calculate it.
The chance of starting kernel position when you have four numbers is, I think, really, really small. 1 over 2 to the 5th, or on that ballpark. So chances are you want to go first to create a kernel position. Like just
If you had to throw a coin, I'd assume we're not in the kernel, but I don't know what the probability really is because I don't think these e's are independent. All right, but let's let it go. We can write a program and test it. So here's what I want to do next. I want to do a reduction, and then I want to talk about the traveling salesman problem and show you an approximation algorithm for it. What we're going to do now is a reduction for the kernel problem. It's a good example of one of these harder reductions where you have to look at the whole big picture. And it's going to be a reduction from 3 satisfiability. Okay, so this time I want to kind of motivate the reduction without an example, then I'll go do an example in just a second. You've seen component reductions like this before, where you have something that represents the variable and something that represents the clauses. So that's what we're going to do here too. And these things are a little bit funny looking. That's the easy part. One of those for each variable. So if you had 2 variables, you'd have 2 of them. If you had 5 variables, you'd have 5 of them. And then for every clause, for every set of 3 that you have in your formula, you're going to make something that looks like this. A little cycle triangle. Three little prongs coming out in both directions. Why do I have 4? 3 prongs coming out in all 3 directions. And then each of these 3 is going to have an arrow that points to the variable in the variable list. So as an example, let's put one more down so we can see what it might look like. If this is x, y, z, this is z bar, x bar, y bar. If this clause was the clause x plus y bar plus z, then this one would go here, this one would go here, and this one would go here. And we would do this for every single clause.
Does y bar need to be coming out of the...
Oh, sorry. Yeah, it needs to go off the prompt, right? So this is like one of these Death Stars. And the ends of the Death Star connect up to the variables on top. We're going to do this for every clause.
Is there an
Teresa.
underlying assumption that you can make a circuit to embody in real life the logic that's embodied in what seems to be any type of picture you want to draw in there to sort of solve these problems? It's like you have a black box, and inside of it you put all these logical connections. But I'm just wondering, like, why you're doing that. Is it going to? It's supposed to be.
Like, why did I make this look the way it does?
Yeah.
Like, where did this come from?
Well, at the end of the day, what good does it do you to have such a?
I'll explain why we have such a weird-looking thing like this.
But it's not based on making a circuit necessarily.
No, no. This was based on a lot of trial and error. And
Nothing in real life necessarily you're going to end up making with that.
no. Well, no.
No. Okay.
No. No. It's just going to end up happening that when you make a graph like this, it's going to have a kernel whenever the formula that it came from will have a satisfying assignment of true and false values.
Okay.
So I'm making up a graph that's going to relate to the formula.
And the graph is just helping you solve logical equations?
Right. If you have somebody who can figure out whether a graph has a kernel, then you can give them this graph. They'll tell you whether it has a kernel or not. And then if they tell you yes, it means the formula that it came from has a true-false assignment. And if they tell you no, it means the formula that it came from doesn't have a true-false assignment. So it's a way of making a connection between a problem that you know is pretty hard and another problem which you didn't know about before, but now you know is pretty hard because if you could solve this problem, you could solve this really hard problem. This procedure that I just did isn't hard to actually do. I mean, you just look through all the variables, make these little edges, For every clause, you make this triangle, then you do the connection. So you can do this procedure fast, so it makes a fast connection between this problem and the kernel problem.
But really, the driving force is the logical formulas, which are represented by circuits in the computer. Otherwise, we probably wouldn't be doing this. And we're just using graph theory to help us solve those series of logical equations.
Well, we're not really solving this because this is a hard problem to solve.
Well, we're determining whether or not we can solve it.
We know we can't do this well. There's actually a lot of research in how fast you can do this. If you go on the internet and look in something called SatLib, they have a big conference once every couple of years that comes up with all the different algorithms people have for really trying to do this and how close they come. And I mentioned there's a 1.33 to the n algorithm that solves this. That's exponential, but it can work in practice for reasonable values of n. So people want to solve this, but nobody knows how. It's a classically hard problem. So here's just another problem that nobody knows the complexity of until someone comes up with this reduction. And now we know that this is hard too.
But the only reason computer scientists care about it is because there's a series of logical equations on the left.
No, computer scientists care about this because it relates to game theory, because it relates to writing programs to solve games. So they're interested in this problem independently. All the other problems, vertex cover, independent set, all those problems relate to things that come up. And we're trying to show that they're hard, that it's not worth trying to...
But the only reason they're interested is whether the computer can model it.
Whether the computer can do it in some reasonable amount of time, right.
And whether the computer can do it is not related to whether you can specify a set of Boolean logical equations.
Wait, I don't understand that last thing you said. Whether...
I'm operating on the assumption the computer we can make a computer to implement logical Boolean formulas. And the only reason you're interested in this game is whether the computer can model it. So it all comes, in the end, it all comes down to a physical reduction.
Yeah, but we can't make the computer do this.
Okay, well, we were just deciding
Right.
whether or not we can.
But no, we're not interested in this just because computers can make Boolean formulas happen. That's not the reason. We're interested in them because hundreds of different problems come up that relate to practical things. And we want to know whether it's worth trying to come up with solutions for them.
But this isn't a math class.
Right.
Well,
Like you're saying, like why do people care about the kernel problem, or why do people care about the vertex cover problem, or why do people care about...
In computer science, what are they ultimately trying to achieve by thinking about these?
They're trying to... You mean, why do people care about solving those problems?
Yeah.
So that's a big question. Maybe what I can do this afternoon is I'll come in and we'll go through a list of practical things that people try to solve that are based on those graph theory questions. But they're... computer scientists are interested in anything that you have an algorithm for. If it's practical, they're even more interested in it. But finding, like, here's an example of an NP-complete problem. I mean, finding... They're interested in these formulas because almost any problem you can come up with, you can describe as a formula. Scheduling problems, knapsack problems, all those things. So, yeah, well, traveling salesman problem. They're all problems that people want to solve. And computer scientists, I'd say the main thing computer scientists are interested in is how to solve problems in an algorithmic way.
Because they can implement it.
Because people want to solve those problems in real life, and computers give them a chance to do it fast. So if you can come up with some way of...
Oh,
Yeah.
just the formulas, okay.
Anyway, maybe I'm not hitting the point, but we can talk later about it this afternoon. So let's talk about this reduction.
Shai,
Yeah.
What is the reduction? It's 3 set to...
3 set to kernel.
And what's the question in the kernel?
Somebody gives you a graph, and they want to know, does it have a kernel? Is there a set of vertices, none of whom connect to one another, but all the ones that are not in that set have a way to connect to something in the
There
set?
doesn't need to be anything about the number of things in the kernel, or the question can
Just yes or no. Is there a kernel? So now maybe we need to do one more clause as an example. Let's do x bar, y bar, and z bar. You'd have another one over here. So there's another clause. All right. To understand why this reduction works, you need to understand why, if there's a true-false assignment here, there's a kernel here, and why, if there's a kernel here, there's a true-false assignment here. There's got to be a one-to-one connection between this graph question about a kernel and this Boolean formula question. So we can go through both directions. We can pick a direction, do that first, and then try to make sense out of it. Todd, you had a question? You thinking? Okay. So what should we do first? If this has an assignment, we'll find a kernel? All right. If this has an assignment, that means somebody can find true and false values for these variables. Let's do it here just as an example. So true, false, true. What we're going to do, if you say a variable's true, let's mark it true, false, true. We're going to put the variables that are false in the kernel. So if you tell me y is false, that gets to be in the kernel. Z is true, so Z bar is in the kernel. And X is true, so X bar is in the kernel. Now I want to convince you that I can go through the rest of the graph and make sure that there's a kernel. One thing you notice is that, for sure, this guy's taken care of, because he points to something in the kernel. So is this one, so is this one. So it's only the nodes in the bottom that have to be taken care of. Let's look at this clause first. This clause points to 3 circled variables. That means those circled variables are all, were they true or false? We put all the false ones in the kernel. So any things that aren't in the kernel are true. If we have things pointing to 1, 2, or 3 circles that are empty, that means there was a real true-false assignment here. Here's a case where we have all 3 pointing to empty circles. If they're pointing to empty circles, then what we can do is just put all the prongs of the Death Star in the kernel. They don't connect to anything because these are all empty, so that's okay. And each of the ones inside the triangle connect towards one of the things in the kernel. So they're okay.
Except that if you're in, say you're in one of the prongs in the kernel, you can. Oh wait, they don't. You have okay. You have the option. I messed up. Who had the control?
If you're in the kernel, you have to move out of the kernel on any edge. Right. And if you're out of the kernel, there must be a way to get into the kernel. So if these arrows point to 3 empty circles, it's quite easy to come up with a kernel. You just mark the prongs on the ends. Let's look at this case. In this case, there's only 1 true value. That gives us much less flexibility. There's only 1 empty circle. So we're going to X that, put that in the kernel. But we cannot put these 2 in the kernel. How come? Because they're connected to things in the kernel. That wouldn't be a kernel. So we're not allowed to use these 2. And now the issue is, can we get a kernel with the rest of the nodes here without using those 2 prong edges? And if so, how do you do it? Well, these 2 are taken care of because they both point to things that are in the kernel. So they're okay. It's just a question of the triangle inside. This one's taken care of because it points to something in the kernel. So we got 2 choices. We'll do this one or this one and see if either one works. If we do this one, then this guy doesn't have any way to get into a kernel. If we do this one, then that's in the kernel, and this can go into the kernel. So now everything's okay. So if there's one thing that goes to a true variable, you mark that true, and you take care of the inside by marking the appropriate one of the triangle. If there's 3 things that are true, you just mark the 3 ones on the outside, and you don't mark any in the triangle. There's another case. What if there were 2 things that were true? What if there were 2 circles? If there were 2 open circles, you'd mark both prongs. Let's say this was an open circle. You'd mark this prong and this prong, and then the triangle one opposite those 2. So if there's 1, you can do it. If there's 2, you can do it. If there's 3, you can do it. What if no matter how you arranged the kernel on top, and you have to arrange it 1 and 1, you have to have at least one of these. You have to have exactly one of these in every kernel. What if you arranged it, and no matter how you arranged it, one of these clauses always pointed to 3 x's? That means one of the clauses was always false. This is the other direction now. What if it's always false? How come you can't get a kernel then? If no matter how you arrange the kernel on top, in other words, no matter how you come up with a Boolean assignment, one of the clauses is all false, that means one of the arrows on one of these clauses, one of these sets of 3 prongs, all point to things with x's on them. What happens then? That means you can't include any of the 3 prongs in the kernel. If you can't include any of the 3 prongs in the kernel, you have to take care of this triangle all by itself with no help from the outside. You can't put 2 of these in because it would violate a kernel. And if you put 1 in, then the one that follows it violates the kernel because there's no way for it to get into a kernel. And there's no prong on the outside that helps it. So there's just enough flexibility to do it when there is a true-false assignment, 1, 2, or 3 trues. But there's not enough flexibility to do it when all the variables end up being false. Now let me stop for a second. This is tricky and complicated. It's an example of a hard reduction. I can see at least half of you don't get it at all yet, and I want to be able to bring you back to ground zero. So let me stop for a second, and then I'll review. Are there questions so far? Yeah, Michael.
What is a move in this? Is going from one node to another a move?
You mean in the game that this might represent? Yes, moving from one node to another is a move in the game.
I see nodes where I would go from a non-kernel node to a non-kernel node. So
that's okay.
But you wouldn't.
You just wouldn't make that move in the game. If you're in a non-kernel node, as long as there's a way to get to a kernel node, you'll take the move into a kernel node.
Oh, okay.
It's okay to have non-kernel nodes connecting to non-kernel nodes as long as there exists a way to get to the kernel node.
Then what about on the right triangle, the bottom left one? How do I?
This guy here?
I go down to a kernel.
No, there might be more than one kernel. There might be more than one. In fact, in this graph, you can see you have some choice. Right. Yeah, Sharon?
I didn't follow on the triangle to the right.
Yeah.
We marked the right node as a kernel node. And why couldn't we get into a kernel just by going up? We were to something that's pointing it into the kernel? Would that be... If we mark the rightmost node as a kernel node so that we could get into the kernel from the top node, why can't we just go up one?
Which one do you mean? You mean this one or this one? The bottom one? This one?
Move up. Yeah. Okay. So we marked the node to the right of that as a kernel node.
Right.
So that node that you're.
So this guy is okay now.
Okay. Now that guy. I guess I don't understand. What is the node above it?
It's not in the kernel.
Okay.
But it's all right because it has a way to get into the kernel.
Pointing to the kernel.
Right.
Okay.
All the prongs that point to things in the kernel are fine as they stand, but you can't put them in the kernel because then you'd have a kernel node connecting to a kernel node, and that's not allowed. But they're all fine as they stand. The ones that go to empty spaces, things that are not in the kernel, they can actually be put in the kernel, and they help you. get these things taken care of, because now these things have ways to get into the kernel. The problem happens when all these three prongs on the outside connect to things that are all x'd. If they connect to things that are all in the kernel. If these three prongs, here, this one connects to something in the kernel, this one connects to something in the kernel. What if this was an x? What if this guy was in the kernel? Then you couldn't make this one in the kernel. And then this node over here would violate the kernel structure because it has no way to get to something in the kernel because you took this one away. These prongs are helpers for the middle ones. If you can manage to cover 1, 2, or 3 of the outside prongs, you're going to be fine to cover the inside. But if you're stuck, not able to cover any of the outside prongs, then you're going to be stuck making a kernel. When do you get stuck not being able to cover the 3 outside prongs? You get stuck whenever you try some situation here on top, and no matter what you try, one of these Death Stars connects to 3 x's. The only way that's going to happen is if every assignment to this formula ends up having one clause with all falses. If there's any assignment in this formula, true or false, that has every single clause having at least one true, I'll use that assignment in choosing my kernel, and then I'll make sure that the 3 x's never occur in one clause, because I'll only mark the falses as x's. So if none of these clauses are all false, none of my Death Stars will go to 3 x's. They'll have at least one open circle. 1, 2, or 3 open circles. A little better?
Yeah.
Almost. Getting there. This is hard, yeah.
It's obviously okay, but
It's obviously okay?
This represents
not obvious.
what I'm about to say.
Yeah.
This represents a game that is very easy to stalemate, because there are a lot of edges that go back and forth between a single node and a
Right,
kernel.
right.
So this isn't necessarily a winnable game.
No, this game has cycles in it. Right.
So
It's saying that if somebody gives you a graph in general with cycles in it, it's not easy to decide whether it has a kernel. Even these very specific, dumb-looking graphs are hard to decide with BMP complete. So a graph in general that has a cycle, there's just no way to find a kernel without trying every subset. And you're right that as far as representing the game goes, it doesn't have much interest. It's just there to show you that the problem's hard. It's not a positive result, it's more of a negative result.
It shows you that the problem is hard with a game with a radically finite number of possible states. There are only a dozen states represented by this graph.
Right, but that's because I use this teeny little formula.
Exactly.
Right,
it's
right.
Still a hard problem with a little tiny thing.
well, we solved it.
Well, I mean, we solved this particular one. Right. I mean, as the number of these formulas gets bigger, the benchmarks in the satisfiable library I told you about, you know, where they have competitions of programs to try to solve this problem, they have a collection of about 600 satisfiable examples. And if you have a program that you think is good, you're supposed to run it on all those and see how long your program takes. So some of them, the hard ones, have thousands of clauses. And that's the thing that's supposed to give you a hard time. You're right. So those would really clog us down. Okay. Are there more questions about this? Anything else I can explain to make it more understandable? Mike? Yeah? All right, so there's 2 parts to this. Again, one is you describe the reduction, and the second part is you explain why the reduction works. You explain why, if there's an assignment of true or false here, it corresponds to a kernel, and you explain why, if there's no true-false assignment, it corresponds to the fact that there's no kernel. If there is a true-false assignment, I set my variables up here in such a way such that the false ones are in the kernel. And then I showed you, therefore, if it's a true or false assignment, there's got to be at least one open circle connected to each of the death prongs. And I can arrange each death prong as long as there's 1, 2, or 3 open circles. But if any way I try to do this, any way I try to get a true-false assignment ends up making one of the clauses having all false, then you pick any way you try, put these x's any way you like, You have to have exactly one x or x bar in each of these clauses to make a kernel. Whatever way you try to do it, that'll correspond to a formula. If the formula is always going to be false, that means one of my clauses will end up connecting to 3 x'd variables. And when you do that, there's no way to take care of the triangle on the inside. So this is just a way of trying to encode the notion of a Boolean formula inside the question of a graph kernel. And it implies that the question of a graph kernel is hard. Okay, anything else about this one? I don't think you'll find this. This is something that I did a long time ago, like maybe 18 years ago. And it's not the published reduction for this problem, because the published reduction is in an obscure place that I could never find. So I needed this for my master's thesis, and I needed to recreate it. So this is just made up. And the only place that I know it exists is in some old master's thesis that I did in 1983 or something. But the actual original reduction for kernel is somewhere else, and I don't know. It's in an obscure journal, and I've never seen it. But it probably looks something like this. There's a lot of different reductions. It's not like there's one for sure. You can come, everybody in class can come up with a different reduction from 3 sets of kernel, and they all might be right. Right? So it's not like you find the one. There's a lot of different ones that might work. We're going to do something different now. No more reductions. Until this afternoon when we do our little group study together. We're going to do a different thing altogether. We're going to talk about the traveling salesman problem, then we're going to quit for today. Traveling salesman problem, TSP. Of all the NP-complete problems, this is perhaps the most famous one. In fact, I brought you a little article from the New York Times. Here, in fact, this is a great way to answer the question you asked me a minute ago, Teresa. This is by Gina Colada, who writes a lot of the science articles in the New York Times, and the math articles. A century-old math problem of notorious difficulty has started to crumble. Even though an exact solution still defies mathematicians, researchers can now obtain answers that are good enough for almost all practical applications. The traveling salesman problem, as it is known, crops up in many practical applications. Take my word for it. From the design of computer chips to the designation of work orders in factories. All right. That's all it says about the applications. Those two things. Work orders in factories. Yeah, scheduling is an example. Brute number crunching by computers can now produce answers to most such problems, even though not an immaculate solution. Quote, everybody likes to point to the traveling salesman problem as a prototypically hard problem, said Dr. David Johnson. He's the author of that Gary and Johnson book. But problems that a few years ago would have made scientists gasp in dismay are now being solved in a few hours of computer time. This is old. This is like 6 or 7 years old, this article. It's kind of interesting, because we're still working on this. The traveling salesman problem asks for the shortest tour around a group of cities. It sounds simple, just try a few tours out and see which one is the shortest, but it turns out to be impossible to try all possible tours around even a small number of cities by enumerating them and looking for the shortest one. It's possible, it just takes a long time. All right, so not such a hot description. For example, if there's 100 cities, there's 100 times 99 times 98 times 97 and so on possible tours. Okay, n factorial. This product is about equal to 10 to the 200th power, or a 1 with 200 zeros after it. To illustrate how long it would take to compute the distances for 10 to the 200th tours of 100 cities, Dr. John Bentley, a computer scientist at Bell Labs, said that if every electron in the universe were actually a computer that could do 1 billion calculations a second, it would take all those computers 10 to the 11th years to finish the job.
Let's get cracked.
Let's make sure we have the best problem before.
In the late 1970s, investigators were elated to solve 50 city problems using clever methods that allowed them to forego enumerating every possible route. By 1980, they got so good they could solve a 318-city problem. In 1986, the record was 532-city problem. Impressive, but not good enough for many purposes. New goal. Now they have solved a 2,392-city problem, and one group is poised to tackle a problem involving 3,038 cities.
Tell them, do they say how to fix the number?
Look at this. Mimicking the language of Iraq's leader Saddam Hussein, Dr. Bentley has begun calling the problem the mother of all algorithmic problems. I don't remember Saddam talking about that at all.
The mother of all battles.
Oh, is that what it is? It's an old reference. You can look at a number of breakthroughs in computer science over the past 25 years and see that they use the traveling salesman problem, etc., etc. It's worth, I made a lot of copies. I'll pass these around. Anyway, what we're going to do today is come up with a method of solving the traveling salesman problem in an approximation algorithm. So we'll get a result which is no worse than some percentage of the best answer. That's so funny.
She's always a shame announcer.
So humorous, funny.
What are the dots?
Oh, you don't want to know. When I made this copy N years ago, whenever this was, I did it on some copy machine that I didn't quite know how to use, and hence the funny-looking things on the side.
What possible mistake could you have made?
It's a belt that drives the thing around, so if you don't cover it up, yeah, good, right. So you actually cover the belt. The more interesting is that I wrote make 35 copies on every sheet. So after just a few generations, we have an exponential number of this copy. All right, so let me tell you. You all know that the traveling salesman problem is NP-complete because it's a general case of a much simpler Hamiltonian circuit problem. If I give you a graph, is there even a way to get through all the cities, yes or no, is a hard question to answer, much less find the one that has the minimum weight. Now that I've said that, when people usually talk about the traveling salesman problem, they're not wondering about whether there is such a tour. In fact, what they usually do is imagine that the cities are actually on a real geographic grid, so it looks like something like this, and that you can actually get from any city to any city. You can take a plane, so that it's a complete graph. All the edges connect to all the other edges. There's no question that there's a Hamiltonian circuit. The real issue is whether there's a fast one. There's one that takes very, very few total weight. And therefore, what you really want to do is just make a little cycle through here, and you can see a little picture on the handout I gave you. It can go jaggedy, but you want the sum of that jaggedy thing that starts and ends back at the beginning to be the minimum weight. Okay, so the normal way is not to draw the edges, just to assume they're all there, and try to find the minimum tour through these points. Okay, so far? So here's a method that will guarantee to get a traveling salesman tour no worse than twice the best one. And it's really easy. It's so easy to describe this method that nobody knows who first thought of it. It's part of the folklore of the research. Everybody seems to have just, when you mention it to them, they spend a couple days, they think of it, and nobody knows who first did it, so nobody published this. There's an improvement on this that I'll talk about, and it'll be the last thing we do today, that is published. And it gets it down to 1.5 times the size. So the method, instead of being twice as bad, ends up just being 1.5 times as bad. And that's good.
Is that what they mean by approximate?
By an approximation algorithm, that's what they need. Something that runs fast and is guaranteed to get the answer within a percentage of the correct answer. There are problems for which you can kind of prove that it's very unlikely to get an approximation algorithm within any constant bound. Vertex cover, it's possible. Traveling salesman problem, it's possible. But for example, 3 coloring is just hard. Say you want to get it with, have so many of the vertices, be off. It's difficult to get any approximation algorithm to it. Let's go back to this. Here's the method. What do you know about a set of points that find something minimum about them? And that's the hint. Their shortest path. What else have we done this year? The shortest path, there's minimum spanning tree, there's vertex cover. That's a hard problem.
Oh, so easy problem?
Yeah, easy problems. So the approximation algorithm for traveling salesman problem is based on the minimum spanning tree algorithm. Here's what we do. We look at this set of points, imagine all the edges are there, and we find the minimum spanning tree. You'll see why in a second. I'm going to make one up. I don't know what the minimum spanning tree is here, and it's hard for me to see, but I think this is the shortest edge. We can try to do it. You can help me a little. What do you think is the next smallest? They're kind of close. Maybe here, 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 maybe here, 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 here. Something like that looks like the minimum spanning tree of those points. We assume that these distances are real life, so that if it's 1 mile to get from here to here and 1 mile to get from here to here, that going directly here is shorter. Okay? So assume that these are real distances. All right, here's the minimum spanning tree. That's the first thing. What do you know about the minimum spanning tree with respect to any traveling salesman tour? Here's a traveling salesman tour. Starts here, goes all the way around, comes back to where you have it, where you started. I'll take away the last edge. That's a spanning tree, right? That's bigger than a spanning tree. That's the minimum spanning tree. So the sum of all these weights is certainly smaller than or equal to this spanning tree. Therefore, it's strictly smaller than this traveling salesman tour. Any tour you come up with, the minimum spanning tree is going to be strictly smaller than that tour, because any tour less one edge at the end is also a spanning tree. So even if that happens to be the shortest one, a tour actually goes one level further and goes longer. So first thing to notice, the minimum spanning tree is strictly smaller than the actual optimal traveling salesman tour. Well, so what? We still don't have an approximation or even any tour. So here's the idea. We're going to come up with a tour that's a real tour, not a tree. And we're going to do it and make sure that it's not any more than twice as big as this minimum spanning tree. And here's how we're going to do it. What's twice as big as this spanning tree? Something that looks like this. I'll make it in a different color. Starts here. What the heck is that? It's a horsey.
Thin horse.
a balloon horsey. This is not a traveling salesman tour. It goes through lots of cities more than once, right? But how long is it? It's exactly twice the minimum spanning tree. Now I know the minimum spanning tree is smaller than my optimal. So I know that this tour is going to be smaller than twice my optimal. Okay? Well, if I can make this into a tour, this walk is at most twice my optimal, because it's twice something that's smaller than the optimal. The thing is, this is not yet a traveling salesman tour, so I'm going to turn it into one. Start here.
Just hop every other one.
Well, I guess until we have to revisit, we're okay. So I'm going to make the green thing mimic. This is fine. We're just going to keep going. No problem yet. Now I have to go back. So what do we do when we go back?
Just go to the next one.
Well, next one's also going back. Just skip. This, good. This is at most the length that it would take to go back, and over, because these are real lengths I'm doing. So I just took a shortcut. So how do I continue? It's okay to continue on the purple lines now, because I haven't visited these yet. But now, I take a shortcut to here, and then I take a shortcut to, because I can't go to here, I can't go to here. Then I can continue on the purple lines, and then I take a shortcut to the beginning. That green line is definitely shorter, certainly no worse, than the doubled purple line. The doubled purple line is no worse than twice my optimal. So the green line is no worse than twice optimal. And you should get this instinct that, I bet if you really did this, you come up with a lot better than twice. And you do. You can come up with pathological examples where you really actually get that 2-factor showing up, but you save a lot by these shortcuts. Okay, are there questions so far? Yeah, Sharon.
How we started out by assuming there were edges between all the nodes.
Yes.
And there aren't necessarily edges.
No, in the real traveling salesman problem, you're given a graph and there might not be edges between all the nodes. And this approximation algorithm really works assuming that there are edges between all the nodes. And it needs that assumption. Yeah, so.
How far off? I mean, it seems like you could actually have far fewer edges, and that would make your approximation algorithm much more inaccurate because you'd be making jumps that you actually can't.
Right. It's not that it's inaccurate. It's that it's not even a tour. You just can't make these jumps if there's no edges there. You're not allowed to. So I don't think the algorithm's even well defined unless we imagine that all the edges are there. So it's not that the result gets worse. It's that it doesn't even work without trying to fix it somehow. But in practice, you really do assume all the edges are there when you're really trying to solve these. When they talk about the 3,000 city example in that paper, they really assume that they're all connected one to another. Okay, other questions about this example? So this is a two times approximation algorithm for minimum spanning tree. What we're going to do now and finish up today is try to make this 1.5 times. This 1.5 times idea is going to be not too hard to describe, but it will need as a piece of it an algorithm that we haven't talked about. So you'll just have to take my word that that algorithm exists. It's the algorithm for matching. I think Mark talked about it briefly during a recitation, but we didn't discuss it in detail in class. So just assume that when I say we can do this part when we get to it, that we really can. Okay, I want to put this spanning tree back on the board. If I can. Does that look like it, more or less? Less, but more or less. Okay. There's the spanning tree we started with. This method that tries to get this factor of 2 down to 1.5 works in a really similar way. It starts with a minimum spanning tree just as before, and it makes note that the minimum spanning tree is smaller than the optimal. Okay, so far. The next step is to look at the nodes that have an odd degree. I'm going to circle them in green. Look at all the nodes that have odd degree. That means, 1, 3, 5 edges coming out of it, 7, 9, etc. One, 2, 3, 4, 5, 6, 7, 8. We talked about this in discrete math, but I'll remind you, you have to have an even number of edges of odd degree. It's impossible to have a graph with an odd number of odd degree edges. You can't construct one. So there's an even number of these. And here's the next step. We're going to take these odd degree nodes and make new edges between them that are going to correspond to the shortcuts that we took in the other example. We're going to do this in a way that minimizes the total weight of pairing up these edges. We're going to take these 8 and pair them up into 4 pairs. And we're going to do it with the minimum weight. This is called minimum weight matching. It's an algorithm that you can do in about n cubed, and we haven't discussed it, but it's doable. So we're going to look at it, assume there's edges between all these green circled nodes, and let's find 4 edges that pair them up into groups of 4 pairs that minimize the total weight. So let's eyeball it and try to make these edges.
Two on the upper right, two on the upper left are diagonal. The two on the
These
top.
two?
Those are diagonal. Those are connected. Those two.
Okay, I'll connect these two.
And the ones to the left of those.
These two.
Probably the ones that are along that edge.
Maybe these two? And
Yeah.
these two?
Yeah.
Okay. Let's say that these 4 edges together pair up these vertices with a minimum total weight. There's an algorithm to do that, and we can run it. So now we don't have a tree anymore. Now we have a graph. What's special about this graph? What's special about the degrees of this graph? They're all even now, because we took all the odd ones and we paired them up, adding an edge. So now we made them all even. What do you know about graphs with all even degree nodes? You can go through every single edge exactly once and get back to where you started. That's why we did all this. Just so that our graph would be what's called Eulerian. So, why do we care about that? I'll use purple now. We'll start at any edge and we'll find the Eulerian tour. Here it is. Okay? By the way, there's no algorithm to find an Eulerian tour because it's completely trivial. Start at any node, leave it, and go to anything that's still open. And keep going until you can't go anymore. You will eventually cover every single edge exactly once. You can't miss. If you want to just build confidence in a child who is kind of losing confidence, say, here's a puzzle, make them an Eulerian graph and say, can you, without removing your pencil, cover all the edges exactly once? And they'll hesitate, but if they just need a little boost, just push them, and they'll never miss, and then you can give them something harder. So here we go. What do we do this for? Now we've, yeah.
I think it's possible that you miss edges, and you have to go back and insert a detour. So if you just keep going, then you create a cycle, but not necessarily an Eulerian cycle.
Is it true? So you can't be completely stupid, you're saying?
You can't be completely stupid.
You can't?
Because you miss, say,
So if you start at node,
Yeah, yeah.
keep going, and it takes you back to the original
look
node.
at 4 paths.
But maybe there are still some edges missing, so you have to go back on your tool and insert the missing detours.
Oh, so maybe I'm, all right. Well,
But it's still easy.
all right, so I stand corrected. It's not trivial, but it's easy. So these kids that I'm trying to boost their confidence they hate me. I think Mark's right. I think it does require a little bit of care, but it isn't too hard to do it. He's right, and we can do it. So here it is. Here's the Eulerian tour of this graph. Why are we doing this? Where is it going? This Eulerian tour is very similar to the doubled purple lines on this one, in the sense that it is not yet a traveling salesman tour. It goes back to the same nodes. So we're going to take this purple tour and fix it by doing the shortcut trick again, just like we did before. So that means I'm out of colors. So now we shortcut over to this one. Go here, go here, shortcut over to this one, and then go here. The blue is a real traveling salesman tour, which shortcuts the purple line. The purple line was an Eulerian tour that we got by adding these extra green nodes. That's a new traveling salesman tour. What I have to explain to you is how big this can get, and why is it only 1.5 times instead of twice? Or why is it even twice? Everybody with me so far? So what's left is the argument as to why this is only 1.5 times. But the method, I hope, is clear. Again, start with a minimum spanning tree. Look for the odd degree nodes. Do a minimum total weight matching, adding those edges. Do an Eulerian tour on the remaining graph. Shortcut it to get a traveling salesman tour. Let's figure out how long that tour can be. Well, the shortcutted tour is going to be shorter than the purple double visit tour. But I'm going to show you that the purple double visit tour is already at most 1.5 times. So we can concentrate on just that purple one. Why is the purple one 1.5 times? How does the purple one relate to the minimum spanning tree?
It's the minimum spanning tree plus the edges between the odd vertices.
Good. Good. Let me say what Michael just said again. Very good. It used to be that the purple things were double the minimum spanning tree. Right? Purple things used to be double. Now the purple things aren't double. They're single the spanning tree, except occasionally they use one of these green edges. The edges that I added to connect the odd degree nodes. But other than that, they just use single spanning tree edges. So the purple double visit tour is going to be no bigger than the minimum spanning tree plus MM, the minimum matching green arrows. Add all the green arrows to the spanning tree. That's my tour that I got. So I got the minimum spanning tree plus this. What's left to do is I have to show you that these green arrows are at most half the spanning tree. Okay, other questions so far? Who's still with me? Nobody? We got minimum spanning tree plus the green edges makes this tour. So if we can just show that those green edges are half that minimum spanning tree, we're okay. Well, they look a lot less than half here. Well, why is it always half? What's the worst that can happen? What do you know about those green edges? What's going on? Can anybody convince me that these green edges are going to be at most half the minimum spanning tree? Or even, maybe you can't do that. Can you convince me that it's at most half the optimal tour? That would be okay too. We know this is at most the optimal tour. If this is at most half the optimal tour, then we got 1.5 times the optimal tour. Why is it at most half?
Because you could break each of the green things into like triangles above it, and you know that would that work? You know, they're shorter.
Actually, they're half-ish. We need to pass through our nodes in our traveling salesman circuit that have odd degree, and we also need to get between them those connected pairs, and so we know that we have the shortest of those pairs, and that's half what we need to cover the whole thing. So it's shorter than traveling salesman.
You're getting there. I think you might even be there. Well, the argument can be said a little more
I'm sure it can.
Succinctly, but it is really a very clever idea, and I think you have it. I'm not 100% sure, but I think you have it. I wrote in blue here all the green arrows, just so you could see them separated. Okay, I rewrote them. This one, this one, this one, and that one. I want to convince you that the total of these weights is going to be less than or equal to half the optimal tour. Okay? So here's what I'm going to do. This is a subset of my graph originally, right? Because there's some nodes that are left out. I'm going to do a tour of this little weenie graph that starts here, goes here, goes here, goes here, goes here. Just any tour of this. Okay? I don't mean any tour. I mean follow the same tour that we did here, making shortcuts if you need to. So we do here, take the shortcut, go here, take the shortcut. Okay? Just do the subtour that only includes the green edges. Now, what do you know about this tour relative to the optimal tour of the whole thing? It's got to be shorter because I made shortcuts. It's definitely shorter than the optimal tour. The thing is, where are my edges here? Notice that this tour alternates edges. Edges that were green, other edges. Edges that were green, other edges. We also know that this collection of edges is the minimum weight collection that pairs these up. Look at the ones that are dotted. They're another pairing up. So which one has to be smaller? These 4 or these 4? These 4, because I calculated the minimum ones. So I got 4 here, 4 here. That means these 4 have to be smaller than half of this whole thing. And this whole thing is smaller than my optimal. So my minimum matching part is smaller than half the optimal. So my whole blue thing that I came up with here is less than or equal to 3/2 the optimal. So this is a tricky version of the original doubling the minimum spanning tree. The doubling minimum spanning tree you'll see in almost every book, and everybody will present it. This is a little less well known. It's originally by a guy named Christophides. I don't know the year, but it's at least 10 years ago. And the trick is to add on this minimum matching idea, leverage an algorithm we know how to do, and gets that factor of 2 down to a factor of 1.5. The description isn't so bad. The analysis is a little bit tricky and clever. But the description itself, just to review, find the minimum spanning tree, take the odd degree nodes, and do a minimum matching on them, adding them in, and making the graph Eulerian, or even degree all around. Run through it with an Eulerian tour, take the shortcuts out to get your minimum tour that way. That's going to be no worse than the minimum spanning tree plus the green edges. The minimum spanning tree is definitely less than the optimal tour, and this collection that takes a shortcut along this road and uses just the green edges that I've rewritten here in blue, this is going to be less than the optimal tour. And the collection of edges that are part of it has to be less than half the optimal tour because I alternate this path, an alternating path, and the ones that are dotted are also a pairing that would have to be bigger than the ones that aren't dotted. So these shaded ones have to be smaller than the dotted ones. That means the shaded ones are less than half this whole thing. So the shaded ones are less than half the optimal. The shaded ones are the green ones, so that this whole thing is less than 3/2 optimal. And that's the summary. Okay, questions about this? Did you do alternating paths? You did the Ford-Fulkerson algorithm, right?
Yes.
That did an alternating path? Oh, no, that's different. But you didn't talk about maximum matching, did you?
Well, about maximum bipartite matching,
but not about weighted matching. Okay. Yeah. I think n cubed is the The best result today is better than n cubed, but you can definitely do n cubed with, with a straightforward algorithm.
This article talks about getting within 2 and 3% of the optimal solution.
Right. And this is still way off from that. Yeah. I don't know what the current results are or what you can provably get, but I'm sure that this article is more reporting the engineering state of the art more than it is the theory state of the art. So I'm not sure how much to trust it. But I'm sure we could go on the internet and find out what the state of the art is on the theory of this. I don't know what it is. Other questions? Okay, so let's plan this. This afternoon, I'll do a little review on a group work together on some of the reductions I gave you on problem set 6. Tomorrow's lecture will be on an optional topic, and unless anybody has a better suggestion, I'll talk about DNA computing. Does that sound fine? Okay, everybody bring in samples of your DNA.